Okay, so in today's lecture, we're going to talk about a new material. It's called a support vector machine. It's a very old method, short for SVM, and has been used for decades before the neural network. So let's just review some and what we already talked about. It's perceptron. Right, so like perceptron right here, we are trying to find some like linear separators. Okay, so you can think about so in this cases for the linear separators, we are so we use the notation slightly different in the SVM settings. In SVM settings, so this is something that is slightly different. That in SVM, we usually move the intercept out. And we assume this class label is to be +1 and -1. So this is like so I'm essentially being the same, but just a different like notations. So the perception here is we have linear separators plus some and the binary step functions. So what does that mean? It's if we're using this notation right here, we have a phi of xw here plus w0. So this is we intentionally separate out this bias out. This will be equal to 1 and -1. This corresponding to class of 1 and class to -1. If xw plus w0 is bigger than 0. I mean, if it is not, you'll be classified as -1. So what does that mean is, so you can think about this as being a linear separators, and only the sign and of this and a separator that and matters in is when we make this like and predictions. So you can think about in 2D plane. I mean, some senses we just draw a straight line here. So this is straight line of x w plus w0 y equal to this. So if we and everything here that is I mean it's above of this line. I mean if we plug in some point that is x and y, if we plug in this formula of this linear separator, it gives you positive values. I'm going to and a category everything right here being in a class of 1. And if we plug in the and this and the linear separator, the value give me negative, so it will be somewhere here. And this will be and a -1 right here. All right, so so this is actually and as I said, the only thing that matters is the sign of this like and the linear separators when we make the predictions. So and that's why so we call the hyperplane xw plus w0 equal to 0. It's called a decision boundaries. Right. So So, but this is kind of interesting. If we have a bunch of data here, and for example, we have like red data right here, and then we have the blue data right here. And in fact, you have a multiple, and this data is like obviously linear separable because you can always perfectly separate these data. If we apply perceptron, it might converge to any of the solution right here. All these lines are good decision boundaries because all these solutions and can perfectly separate blue points and red points. Because if we using this optimization problems, it always give me global minimum to be 0. So that means we can we perfectly separate things out. But the issue is all the line and all the separators being the best, right? So I mean, is it true? So let me just using some figure to illustrate this idea. For example, right here. So these are the 4 figures. And these like black line right here separate these and the blue and the red points. And obviously the first one is really bad because this doesn't even perfectly separate the blue and the red. So we get rid of the first one. But the other 3, the second, third, and fourth, all of that actually perfectly separate the blue points and the red points. So which one is better? Right. So this is a question: is if we have a multiple choices of and decision boundaries, which one is and better? So one way to think about it is I want to find the one that is most stable under perturbation of input. And what does that mean? That means if we sample more points, I mean, it could be some testing data set that is slightly off the current domain that we have. And for example, right here, if we have a point right here, then under this line, it will be classified as red. But with our common intuitions, if the point right here that is really close to this blue cluster right here, it should be classified as blue. Same here, if I have a point right here, it's supposed to be classified as red, but from this decision boundaries, it will be automatically being classified as blue. So you can see this is not really good because if we perturb the data a little bit, it will it will create a lot of misclassifications. On the other hand, if we are working on this one, I mean, no matter how you perturb, I mean, as far as this perturbation is small, if I put the point right here, it will be, it will still be classified as blue. If I put point right here, it will be still classified as red. So, and basically it will not change the fundamentals of the problems. So you can see if you are being asked which one is the best, it turns out the fourth one that we have is the most robust one. It is stable under the perturbations of the input. So like if we want to find the line, it will be this line will be the best if we can. All right, so this is very intuitive. Can we formulate this idea into mathematics? So what does that actually mean? And if we have a point right here and a bunch of point right here, if I bunch a point right here, and what do you mean by I draw a line that? So and draw a line that is, so in some senses, this line is good because it gives the largest margins. So meaning that so there will be no instances land within this margin right here. So you can think about this is like my right margin. So this will be my and the left margins right here. And you can see right here, this is my margins. If we choose this is, decision boundaries, this margin will be and really big. On the other hand, if we choose another decision boundaries like this, so then the margin, like right margin will be here, the left margin will be here, then the margin right here, and you can see will be significantly smaller than the black lines. Okay, so this is something called hard margin classifications. So we want to give, the one, and we want to find out, if we have like multiple ones, then can separate these and the data point, then we choose the one that give the largest margin. So this is called hard margins class and hard margins classifications. Hard margins. So this and specifically, we want to create the largest margin as much as possible. And how to do that? So this is something that we need to, and we need to make it sure. So the first thing we need to assume and make like bunch of assumption here. So assume these data points are separable by linear functions. So, if it is not separable, then we cannot talk about the largest margins at all, right? Because this is always, and the margin will be 0. So this is something that we need to assume, and then not always we have that kind of situations. But if some data are not linear separable, we might, and what we can do is we can lift up into high dimensions. It might, so it might give you like linear separable situations. And also, so this give you, and also we need to have some unit length vector of the hyperplanes. So and then let me just show you what is things that we are looking for. So I'm going to draw a picture right here. So I have some like red points here. I have some blue points here. So basically, ideally, I want to choose like an decision boundaries like this, because we can just like literally shift this boundaries to the left and to the right. So this is basically the decision boundaries that somehow we want to maximize. This is equal to 0. And this dashed line is on the margins right here. And also, and I want to emphasize, let me just. So this is an expression for this line. And of course, we can always multiply a constant. This will be the same line right here. This actually defines the same plane. So what does that mean? If we have the freedom to choose the norm of the W. So that means we have freedom to choose the norm of W. So we can make it larger or make it smaller. And also, and what we can do here is, and we can make like an unit vectors of these hyperplanes. is xw plus w0 equal to 0. So this is basically my hyperplane. So we can define the unit vector. So you can define the unit vector like this. Is I'm going to call it n is equal to is in the direction of so directions of of the vector of w. So it's w divided by the norm of w. Okay, so you can think about this way. So this is basically the unit length and vector of the plane. So this is the first observation. This is second observation. So that means we can always normalize it and the hyperplanes, and we have like freedom and to choose of the norm of w, and you can choose simply just and a norm of w to be 1 if you need it. And also this third definition, that is the examples actually closest to this decision hyperplanes is going to be called support vector. So this will be your support vector. This will be your support vector because this is the point that actually closest to this decision hyperplanes. So without losing generality, we can as I said, we can always multiply and a constant and to make it and to satisfy certain values. So we can assume this is and this support vectors and these support vectors what lies on the hyperplane of x times w plus w0 equal to plus and minus 1. So here we call the margin boundaries. Right, so this is obviously, so it's very important. You can think about and this and you can think about this like and everything going down right here. This will be x times w plus w0 is equal to minus 1, and everything up right here, this will be plus 1. Okay. All right. So that means this is, and these points are actually closest to this and the decision boundary. So this is so my support vectors. So that means everything that other than the support vectors and all examples other than and the support vectors has to either bigger than 1 or less than minus 1. Or minus 1. So, and this is basically coming from the definition of the support vectors. Next, number 5. And then we need to define the distance because we want to make sure our margin is to be largest. So that means we need to define the distance from any point to this and the decision boundaries right here. So, and for example, if I'm giving a point right here and I need to calculate this distance to this decision boundaries. So if you are given for any point of x right here, the distance to the linear separate and the decision boundaries or the linear separator and it depends like how you call it. Is, I'm gonna call it R, is xw plus w0, and it divided by the norm of w. Okay, so I mean, this is how you calculate everything right here. And also, and the key here, and we assume everything is on the support vectors. It's +1 and a -1 right here, right? So this is where the like and the support vector is slicing. So that means if that's the cases, so I mean, I'm gonna call this the whole margin right here. So I'm gonna call this row here. But we know the distance between these and these two margins. So I think that's what I called, right? So, and the distance between and from support vector to the separators is, so distance between two margins. Two margin line. So one will be, so I'm gonna call it row. This is just, so this is 1 to the 0, so this is 0, and -1 to the 0. So basically, the distance will be just being 2 if we plug in this and the value right here. So this will, and sorry, 1 over, and this plus 1 over of this. So this is basically the left and the distance between the left margins to the decision boundaries, and the right margins to the decision boundaries, and both are 1 over and the norm of W. So I mean, total that would be 2 over the norm of W right here. So that's the margin that we want to maximize. So we want to maximize. So that's something we want to maximize right here. Okay, so let's just set up mathematically. So we give like a lot of an analysis in terms of and the data that we have. We define a lot of things. We define the linear separator. We define margins. We define the equation for the margins, and we calculate distance between two margins. Right. So this is the thing, and by the end of the thing that we are interested in. Okay, so here is the setup. Here we go. So setup is we are giving some like linear separable training data set. D is training data set. From 1 to the n. And this x of I is usually in R small d. This is yi, as I said, is between +1 and z, and it's either +1 or -1. So these are the values that are being set up here. So the key here is for some constraint, so we know I want to find out a W such that if xiw plus w0 is bigger or equal than 1, then everything here will be classified as 1. So okay, so I forgot to mention, I think we already mentioned this, and that this data is linear separable. So this is some assumption that we already have. So we know if we train with the perception, it will end with like global and minimum equal to 0. So, and we have a perfectly separate and everything here. All right, so this is one here, and of course, if this is less equal than -1, then yi is equal to -1. So this is basically says, and everything above, everything above, the margin of an x w plus w0 equal to 1, that I would classify this point to be 1 and vice versa. And you can write everything uniformly. So uniformly. So it can be written as follows. So yi and x of I w plus w0 is bigger equal than 1 for any I. Right, so this is obviously very important. So that's the constraint that we need to satisfy to ensure we perfectly separate and these data from red and the blues. And also we need to find the maximum, and that's the constraint we need to find and maximum margin solutions. So that means we need to find maximum margin solutions. So this is basically says I want to find out my w and the w0, which is my vector, and I'm intercepted is to maximize my margin. This margin is equal to 2 over the norm of w and is subject to my constraint. Okay, for any I. Or sometimes it will be easier, we can formulate everything in terms of the minimization. So this is minimization of w and w0, or 1 over 2. The 2 normal square subject to yi, x of I, w0, bigger equal than 1 for any I. So this is something called quadratic programming. If you have already and heard about this, so this is, we have a quadratic objective. And we have linear constraint. So this is something called, and you can show this whole thing is, basically a strictly convex problem. So what does that mean? It has a unique global minimum. If provide all these data as linear separable. So this whole thing, and it can be solved with all these existing like quadratic programming solvers, for example, can solved by something called CVX and OPT, some quadratic programming problems. But there are some other methods that we can solve that without using this quadratic programming. And turns out this is more insightful if we need it. And also, that's the training part. So this is basically the training part. And not only on the training, we also need to write the predictions. Right. So for example, if you are giving a new data, and we need to predict a class. So basically, if we already find this optimal and a W star and a W0 star, we can predict. And with the new data, and we have a new data, say X. So we can predict the class Y is being the sign of this linear functions. Right. So if it is positive, it will be +1. It will be negative, that will be -1. All right. So this is a simple an introduction right here. In the next, we are going to using another methods to solve this problem, other than and to solve this CVX OPT. We are going to using like Lagrangian and of the primary problem to create a new problem and to solve everything and accordingly. So this is something that is being taught in optimization. So and I hope this will be a quick review of what we already been done before. But if you haven't or you are not familiar with that, so this will be something that you need to and understand and to learn with that. Okay, so stay tuned for the second part.